Problem statement is given. The A992 steel rod is subjected to the loading shown. If the cross-sectional area of the rod is 80 millimeters squared, determine the displacement of B and A. Neglect the size of the couplings at B and C. Okay, so let's start off with A. So we want to look at point A, or this little area around A, and we want to see exactly how it's going to be displaced due to all of these external forces. And how are we going to do that? Well, we want to look at mainly the internal effects due from the external effects. So what do I mean by this? Well, it's going to take some statics for us to figure out these internal loadings. So let's go ahead and do that. So if I go ahead and let's say I draw a cut right here, or if I make a cut right there at in between A and B, and we go ahead and find the axial internal loading over there. So I know this is not a straight bar, but don't mind the drawing. Just trying to exemplify the concept here. So this is 10 kilonewtons down here, right? This is our point A, right? We're going to cover everything from here up, and we're just going to look at this part right here. So this is 10 kilonewtons going down this way. Now, what happens when we cut the bar? We get an NMV, right? We have a normal force, we have a shear force, and we have a moment. But as we see here, there is going to be no shear force and no normal forces, at least for this section. And we're only interested in looking at the normal force anyways. So here we're going to draw our force, internal force. I'm going to call this, and I'm going to call it NAB because it's in between points A and B. So this is true for wherever you cut along this bar between A and B. So we can go ahead and surmise that NAB using equilibrium is 10 kilonewtons. All right. So that's great. Now let's cut over here now. We want to cut between B and C. What happens when we cut here? The internal effect is going to be different. So let me go ahead and draw that. And I'm going to go ahead and draw down here our next beam. So this is our rod of the cut that we just made now. Okay, let me make a better rod right here. It's not going to be perfect, but you get the idea, right? So here we're going to have our 10 kilonewtons at the bottom. Remember, this is A. And then somewhere around here, there's going to be two forces coming out like this that are pulling on the rod. And they're both 5 kilonewtons. And this is a 3, 4, 5 triangle, right? So I'm going to draw a little 3 and a 4 right here to kind of show that this is the 3, 4, 5 triangle, or the component at least. All right, and as I said earlier, we're only interested in the axial loading internally. So we're going to just go ahead and draw our N right here. So I'm going to call this NBC because this is going to be true for anywhere you cut in between B and C. So let's go ahead and do our equilibrium equation to solve for NBC. So NBC, let's see what that is. So we do the sum of our forces in the y direction, and sum of the forces is equal to 0. We go ahead and do this. So negative 10 minus 2. Now we're going to see that these forces are identical in the y direction, right? If we draw our axis to be like this. So minus 10 minus 2, 5 kilonewtons. And the component in the y direction is 4/5 because we have our 3, 4, 5 triangle. So it's 4/5, and then our NBC is in the positive y direction. So go ahead and write that. NBC is equal to 0. So that's finishing our equation. And if we go ahead and solve for NBC, just do some algebra. We go ahead and see that NBC is going to be 18 kilonewtons. All right. So now that we have that, I'm going to actually underline these so that way I can reference these later. So we have NAB 10 kilonewtons, NBC is 18 kilonewtons. Now, should we find out what this is? I think we should find out, right? Because we want to pick a reference point where something is not being deflected or something that's not going under elongation. And in this case, D is going to be stationary. So we want to make sure that we get all the internal loadings all the way from here because we're going to start from D and we're going to see how much A has elongated from this rod, entire rod. So that's the idea here. So let's go ahead. Now we're going to go ahead and find the internal effect between C and D right here if we cut right there. So let's go ahead and do that. I'm going to go ahead and make a big space here because this is going to be a big long beam. And okay, no. I should probably incorporate straight lines for this, but I'm going to do my best with my own abilities. Okay, there we go. So this is, again, 10 kilonewtons. And over here, we're going to have our 3, 4, 5 triangle of our component, 5 kilonewtons this direction, and 5 kilonewtons in this direction. And then over here, we're going to also include this, right? So we have the 6 kilonewtons due to a component 45 degrees from the x-axis. So it's going to look something like this. I'm going to draw 45, or I'm going to write that down here. So 6 kilonewtons. And then the same idea here. This is 6 kilonewtons. 6 kilonewtons. And then over here we have a 45-degree angle. Right? We're seeing a bit of a pattern. We're seeing a bit of a symmetry here. And then, of course, our normal force subject to the cutting, and we'll call it NCD. All right, so now let's go ahead and write our equation of equilibrium in the y direction to determine NCD. I'm going to write that below this statement right here. So we're going to have NCD, and then all of these are going to be negative, right? So we're going to have minus 2, because we're going to have 2 of these guys going in the negative y direction. So 2 of 6, and the component is sine of 45 degrees. But if you remember our unit circle, what is sine of 45 degrees? We can actually just rewrite that as root 2 over 2, right? That's equivalent to sine of 45 degrees. And then over here, we're going to have, again, minus 2. And remember, this is the 3, 4, 5. I know it doesn't look up to scale, but that's what it is. So 2 times 5 to the 4/5. That's our component. Minus 10 is equal to 0. All right, so now we're going to go ahead and solve for NCD. So if we go ahead and solve for that algebraically, we should get that NCD is equal to 26.485 kilonewtons. All right. So just going back, take a step back. We have solved for all the internal loadings across this rod. Now we're going to go ahead and do our analytics. So we're going to go ahead and solve for the elongation at A and at B, which is what the problem was asking. Or sorry, the displacement, which is essentially the idea that how much is A going to be displaced after it is subjected to all of these loadings. Okay, so let's go ahead and do our analysis here. So I'm going to go ahead and draw a big line. So now, remember our equation from chapter 4 from the Hibbeler's book. We go ahead and look the deformation or the displacement at a specific point. So I'm going to say that we're going to look at point A first, right? We're going to see how much it is displaced downwards. And we know it's going to be displaced downwards because obviously we have all of these loadings pointing down. It's point A is going to be displaced due to tension. So we know that for a fact. Now what's the equation for this? It is going to be all of the sums. It's going to be all the sums of our normal forces times the length at that given point. And then we have the area of the cross section times the elastic modulus, which we can actually find that in the back of the book. And I'll go ahead and write this here. A992 steel, the Young's modulus for that is 200 gigapascals. So I'm going to go ahead and write that here, but you can find this in the back of your book. At least for the Hibbeler 10th edition, you can find that there. Actually, I didn't mention this, but this is actually a problem from the 10th edition of the Hibbeler's book. So just keep that in mind. Okay, so let's go ahead and do this. So we want to evaluate where all of these sections of the rods are being elongated here. So we know, starting from point D, right? We know that point C is going to be elongated due to an internal effect that we had found. And then so is point B from this distance to this distance. And then so is from B to A. So essentially we're going to have three summations of our elongations here. So we're going to end up getting this. So let's start off with from D to C. What was the internal force from D to C, right? It was 26.485 kilonewtons. Now, I cannot stress this enough. You want to make sure that the units are consistent. So what I always like to do is make everything in newtons. That way it makes your life a whole lot easier. So I'm going to convert this kilonewtons to newtons. So 26.485, we can convert that to 26,485 newtons. And this is rounded, by the way. The decimals could have kept going, but I'm rounding this up here. And what's the length of this distance? So from D to C, it's 0.75 meters. So I'm going to go ahead and write 0.75 meters. Okay, and do we want to convert this? No, because newtons and meters are kind of like peanut butter and jelly, so they go hand in hand with each other. So I'll keep that as meters. And then the area of the cross section, that was given in the problem statement, actually. It's right here, 80 millimeters squared. Now that is not in meters, so that's not consistent with what we have here. So let's go ahead and convert that. So 80, right? Now millimeters squared is equivalent to 10 to the negative 6 meters squared. And then, sorry, that is a bad written version of an M. All right, and then let's go ahead and write for our, what did we say our Young's modulus was? We said that was 200 gigapascals. So that is this guy right here. So 200 times 10 to the 9th pascals, right? So that's to keep all of our units consistent. And that is a terrible 9. I'm just not able to draw on this for some reason. All right, let's see if we can do a better job. There we go. So that's our first one, right? Now, we also want to keep in mind the sign convention. So since we said that in tension, the sign is positive, right? Because we found all of our internal loadings to be due to tension, right? This is in tension, this force is in tension, and this force is in tension. Just look at our free body diagrams, and you'll see exactly why all three of these forces are in tension. So since they are all in tension, the sign convention for all of these are going to be the same. So let's go ahead and do the displacement between C and B now. So what did we say that force was? We said NBC was 18 kilonewtons, so we have 18, equivalent to that is 18,000 newtons, times the length, which is 1.50 meters, so 1.5 meters, divided by, now A and E are going to be the same throughout the entirety of this rod, right? Because the area of the cross section does not change, right? And then E is going to be the same because the material throughout this rod is steel, A992 steel. So I'm going to go ahead and save us the trouble. It's going to be the same thing as this denominator over here. I'm just going to rewrite it as AE. And so we should see when we do the third displacement from B to A. Let's get that force. So where did we say that? Oh, right here. This was the first one we did. So NAB is 10 kilonewtons. The equivalent in newtons is 10,000, 10 to the third, times the length of that. So from here to here is 1 meter. So I can go ahead and just write 1 there. And all that's divided by AE. And if we go ahead and plug this into the calculator, I went ahead and did this already. So you might go ahead and take some time to do this, but I'm going to go ahead and pause the video so you can do the calculation, but I'm going to go ahead and write it right here. So I ended up getting that the elongation at A is equal to 3.55 millimeters. I went ahead and converted back to millimeters. You're going to get this in meters, but just convert it back to millimeters. It honestly doesn't matter. But to keep consistency with the sig figs, I put it in millimeters. All right, so now let's go ahead and find the displacement at B, delta B. So let's go ahead and analyze what we're looking at. So B, right? Starting from stationary point D, we're going to see that point C is elongating and point B is elongating. And that's it. We don't need to look past whatever's beyond B because we're not interested in A now. We're interested in how much B is going to be elongated. And point A is independent of that displacement for B. So it's kind of like, think about it like this. If you have a rod like this, and you want to displace something, and let's say that this is fixed, right? So this is going to be fixed over here. And you want to pull at this point right here that I just drew. So let's say I go ahead and pull at this point. Now we know that from this fixed point all the way to this point, it's going to be deformed, right? But this part right here, from here to here, is not going to be deformed. So that's the idea that we're going to see here. So honestly, it's basically just going to be this portion right here. It's basically A, but we're not looking at the portion that's from B to A that's being displaced. So if we go ahead, I'm going to go ahead and rewrite that here though. So 26,485 times 0.75 divided by AE plus 18,000 times 1.5. I'm sorry that my handwriting is a little sloppy. I'm just trying to write a little bit fast so that the length of the video isn't too long. And to save time, go ahead and plug that in a calculator, pause the video, whatever you need to do. The answer for this is going to be 2.93 rounded millimeters. So, to recap, now this makes sense, right? Because we know if we're going to elongate or displace certain parts of the rod right here, we know that C is going to be displaced a certain amount, B is going to be displaced a certain amount that's greater than C, and then A is going to be the greatest. So that makes sense that A is going to be displaced more than B. Now, what is C? They didn't ask us for this, or that wasn't in the problem statement, but if they did, we would know that delta C would have to be less, oh, I wrote delta B. Whoops. Delta C would have to be less than delta B, because you're only going to be looking, in reference to D, you're only going to be looking at how much this has deformed. All right, well, that's all I got for the video, so thank you for watching.